These are my notes on covalent bonding, which are a little bit different than maybe the note packet, but it tells you everything that's in the note packet as well. Covalent bonding is going to take place between two or more nonmetals only. So the key with that is there is no metal present in covalent bonding. Nonmetals are going to share electrons, so they share electrons to form molecules. Covalent bonding is represented by Lewis structures. So I need you to kind of back up and recall that when you have a hydrogen and you look at how many valence it has on the periodic table, hydrogen has only one valence electron. And so because that is one single electron, it's able to create one bond with that electron with another single electron with a neighboring element. So it's going to have one bond. So a bond is made up of two electrons that are shared. So if you'll notice here, we've already written hydrogen can make one bond, typically. Next we'll look at, so we're going to not worry about the boron atom, even though by an exception it tends to only make 3 bonds, but we don't have to worry about that one. Carbon is going to have a tendency to make 1, 2, 3, 4 bonds with its single electrons, and the 4 bonds can come in various forms, such as you can have 4 single bonds, or you can have what's called a double bond and 2 singles. It's still a total of 1, 2, 3, 4. Or you can have a triple bond with 1 single, and it's still a total of 1, 2, 3, 4 bonds. So carbon can make a total of 4 bonds. There's one more scenario that's not shown here, that carbon could also have a double and another double. Again, a total of 1, 2, 3, 4. And so you can have this also, so you should add that to your chart. Okay, now nitrogen is going to have 5 valence electrons, which means that it can form 1, 2, 3 bonds. These are not going to bond because they are already paired with each other, so they're going to form what's called a lone pair or an unshared pair of electrons. They're not shared with another element, they're just paired up together on this element. But these will be shared electrons, shared pair of electrons, because there's 2 electrons that'll end up in each bond. So nitrogen is going to have 3 bonds, 1, 2, 3, and 1 lone pair or unshared pair of electrons. And you'll notice that I kind of drew a bubble around it. I like to call that an alien head because it's staring right at you. So when you have a lone pair of electrons on the central atom, then I tend to draw an alien head or a bubble around them. Okay, so because nitrogen can make 3 bonds, that can come in a few forms. We could have 1 double, 1 single, or we can have 1 triple. But in all 3 cases, you have 3 bonds total and 1 pair or lone pair of electrons on the center atom. The oxygen atom has 6 valence electrons, which means it has 2 lone pairs and has 2 singles that can form 2 bonds. And so typically, you're going to see oxygen has 2 bonds and 2 lone pairs, or a double bond and 2 lone pairs. Finally, this X represents any of the halogens on the periodic table, and I'll just focus on chlorine in particular. It has 7 valence electrons, so it has 3 pairs that are not going to bond, but it has this 1 single that can bond. And so all halogens will tend to make 3 lone pairs and then have 1 bond between it and another element. So now that you have an idea of the common bonding patterns of elements, then you can kind of use your periodic table to help you see them. Where hydrogen is going to have 1 single bond, we're not going to worry about lithium, beryllium, or boron. And then when you skip over here to carbon, there can be 4 bonds. It's in group 4. It can make 4 bonds. Then nitrogen is actually in group 5 on the periodic table, but if you recall, nitrogen tends to have, no, I'm not going to say that. Nitrogen is, so it's going to go from carbon, you can make 4 bonds, and then it goes 3 bonds, 2 bonds, 1 bond. But all atoms, the purpose of bonding is having 8 electrons around it in total. So these dashes are 2, 4, 6, 8. For nitrogen, we have 2, 4, 6, and we need the pair to make 8. For oxygen, we have 2, 4, and then 6, 8 with the pair. And then fluorine, it's 2, 4, 6, 8 with the 3 pairs. And then, of course, noble gases don't need to bond technically in order to form their octets. They already have them. So Lewis dot structures for molecules, you can show them with dots where you're showing a pair of electrons, one from the hydrogen, one from a neighboring hydrogen, and then they share the two of them by overlapping their electron clouds to each other. And so this is a shared pair of electrons, which we represent typically with a dash, which shows the two electrons that are shared between them. So always know that the line between one element and its neighboring element represents two electrons that are shared, two shared or bonded electrons. And then if you have a pair of dots, those are known as a lone pair or unbonded or unshared electrons. Next, let's talk about Vesper Theory. It stands for Valence Shell Electron Pair Repulsion Theory. And what it means is pairs of electrons will repel, push as far away from each other as possible, which affects the shape of the molecule. For example, here's your atom in the center, and then let's say we have two elements bonded on either side of the central atom. Well, the farthest apart that they could possibly be from each other is 180 degrees. So in other words, I could have my central atom, and then if I had only two atoms bonded to that central atom, they wouldn't look like this because of the repulsion that they have against each other. The farthest they could be from each other is this 180 degrees both ways. So that's 180, and here is 180. So that is as far apart as possible that the surrounding atoms can be from each other, which creates this straight line shape called linear. If you have three bonded atoms around the central atom, then the farthest they can be from each other is 120 degrees. And so each of these angles is 120 degrees, and so that's the farthest they can be from each other, and this is known as trigonal planar. And it's actually flat in the plane. A bent shape looks like this, where the bonded atoms, because there's a lone pair on the center, it's pushing down on the bonded atoms, and so it's making it look bent. So instead of a straight line, the bonded atoms look like a bar that's been bent because that lone pair is pushing them downward. Okay, next is tetrahedral, which is when you have one single atom in the center and four things around the center. So here is tetrahedral, one bonded atom in the middle, 1, 2, 3, 4 surrounding atoms. These each have a bond angle of 109.5. You don't have to know bond angles in this course, but I'm just telling it to you. Now, if we have, instead of this atom, we have a pair of electrons on the center, that's going to just take these and just kind of push them toward each other. So this will be called Trigonal Pyramidal, because if you ignore this, it looks like they make a triangular pyramid base. Okay, and then over here we have, instead of one lone pair, now we have two lone pairs, and that's going to push these two atoms toward each other, and so you can see these look like they are in a bent shape. So technically there are shapes that go all the way to 5 and 6, what's called domains, but in this course you are only responsible for those up to this point: tetrahedral, trigonal planar, bent, and linear. So those are the only ones that you're required to know for this course. Oh, and also you should know trigonal pyramidal and bent. My apologies. So everything from 2, 3, and 4 you're required to memorize for this unit. So we've already discussed this, but a polar covalent bond is when clouds overlap, but the more electronegative element has a stronger pull, so it's an unequal sharing. Bonding electrons are in a tug of war. Note the slightly positive and slightly negative ends here. If you have nonpolar covalent bonds, the clouds overlap, but the elements are equally sharing the electrons, which gives them equal-sized clouds. Subtracting electronegativities is how we determine if you have a polar or nonpolar covalent bond. So now we're going to draw Lewis structures, and then afterwards we're going to kind of analyze them. How many lone pairs are on the center? What's the shape? Are the bonds between the atoms considered polar or nonpolar? So first, you want to add up total valence. So in my first example, we have H2, which is hydrogen, and hydrogen is in group 1. It has 1 valence. And since I have So I'm going to say 1 valence times, there's 2 of them, so that equals a total of 2. That means that in our structure, we should have a maximum of 2 electrons in the drawing. Now we're going to use common bonding patterns to bond atoms to each other. It's a hydrogen and another hydrogen, and we know that hydrogen will tend to make one bond sharing it with one other atom. And so since both hydrogens tend to make one bond, that's all they're going to have is one bond between them. And now, if we check octets or duets for hydrogen, if we need, we add dots around the atoms. But we don't have to do that because hydrogen only needs 2 electrons and we can only have 2 max in the structure. That's 2 electrons. This is the Lewis structure of H2. How many lone pairs are around them? None. What's the geometry? We don't really usually do geometries for these because they don't have a central atom. Technically, we can call it linear, but you're not going to be asked for a geometry for this. Okay, but you should be able to tell, are these bonds polar or nonpolar? Since both of these atoms are identical, they are nonpolar bonds. Okay, let's do N2. If I add up the total valence of nitrogen, it's 5. So it's 5 times the subscript of 2 equals 10 total electrons that I can have in my drawing. So now I have 2 nitrogens. I'm going to draw N, N. And then what is the common bonding pattern for nitrogen? Nitrogen needs to have 3 bonds, 1 pair. So how are we going to have 3 bonds if there's only 2 of them? Well, that means that only between these 2 we're going to have all 3 of the bonds, and so it's going to be a triple bond. Remember, each nitrogen should also have 1 pair, and so we add the pair, 1 on each nitrogen. Now, if I check my octets, this nitrogen has 2, 4, 6, 8. This nitrogen has 2, 4, 6, 8. And then my total in this whole drawing is 2, 4, 6, 8, 10. So my total is good. Same was over here. And so this is going to be the Lewis structure. We're not going to worry about how many pairs there are. I mean, I guess we can. There's a pair here and there's a lone pair here. So there's 2 total lone pairs. But usually we only worry about that around the central atom. And there's no central atom here in the diatomic. What's its shape? We're not going to worry about that. And then is the bond polar or nonpolar? Since both of these are identical, it's nonpolar, the bond between them. Okay, so for oxygen, oxygen has 6 valence electrons. And so it's going to be 6 times 2 equals 12 electrons. And then it's an oxygen hooked to another oxygen, but we need to look at the common bonding pattern for oxygen. Oxygen should have 2 bonds, 2 pairs. And since there's nothing else to bond with, they're going to just make their 2 bonds with each other, and then they each have their own 2 lone pairs on them. And so it's going to be a double bond between the 2 oxygens. So number of lone pairs, there's a total of 4 here. We're not going to worry about the geometry. Since these are both identical, it's nonpolar. And now we're going to check our octets. This oxygen has 2, 4, 6, 8. This oxygen has 2, 4, 6, 8. Everybody's got an octet. Do we have 12 total in our drawing? 2, 4, 6, 8, 10, 12. Yes, we do. And so this is the correct Lewis structure. I'm skipping down because iodine is going to be just like fluorine, chlorine, and bromine, which is the row above. So first of all, I'm going to look up iodine is in group 7, and so it has 7 valence electrons. So it's 7 times 2 equals 14 total. And we just have 2 iodines, so it's going to be an iodine hooked to another iodine. What's the common pattern for a halogen? Halogens are going to typically have 1 bond, 3 pairs. And so there's only going to be 1 bond, and then we're going to have 2, 4, 6. That's 3 pairs. 2, 4, 6. And now, if we check our octets, this iodine has 2, 4, 6, 8. This iodine has 2, 4, 6, 8. And then our total, we should have 14 total. 2, 4, 6, 8, 10, 12, 14. We do have 14 total, so that's good. So total number of lone pairs, we have 1, 2, 3, 4, 5, 6 of them. Don't worry about the geometry because these are identical. It's nonpolar bonds. Now let's look at this one. This one's new. It's different. HF. So H has 1 valence and F has 7. So it's going to be 1 plus 7 equals 8 electrons. Now, it's just an H bonded to an F. And now, what are the common bonding patterns? Well, the hydrogen should have only 1 bond, and the fluorine should have only 1 bond, and they do. The fluorine also should have 3 pairs around it. So 2, 4, 6. All right, so now we're done with our drawing. Hydrogen can only have 1 bond, so 2 electrons. That's good. Fluorine should have 2, 4, 6, 8. That's good. Now let's check our total. If we add up everything, we have 2, 4, 6, 8. So that is satisfied as well. We have 3 lone pairs. Don't worry about the geometry. Since these are different, they're going to be polar. That's kind of the quick way to tell that. Okay, so I'll let you do HCl. It's going to be similar to HF. Now we're going to focus on drawing the Lewis structures for these non-diatomic molecules. So they all have a central atom, and everything else is bonded around the center. So the first thing I'm going to do is add up the valence electrons for each element by looking on the periodic table. Carbon is in group 4. It has 4 valence, plus hydrogen has 1 valence, times there are 4 of them. And so this is equal to 8 electrons. That's the total I can have in my drawing. Now I'm going to put my central atom, carbon, and then it's surrounded by 4 hydrogens. So 1, 2, 3, 4, and all of them are hydrogens. Go ahead and know that hydrogen can only have 2 electrons in 1 bond. So each hydrogen is fine. Make sure you have an octet around everything else. So carbon here has 2, 4, 6, 8. That's an octet. We're good. And then the total number, let's check it. 2, 4, 6, 8. The total is also good. There are 0 lone pairs on the center atom. So when I want to look up the molecular geometry, I want to note that there are 1, 2, 3, 4 bonded atoms around the carbon. So 4 bonded atoms, 0 lone pairs is going to be tetrahedral. So this is tetrahedral. And because the bonds are, the carbon and hydrogen are different from each other, these bonds are going to be considered polar. Now, here carbon has 4 valence, plus chlorine has 7 times, there's 4 of them, and so that's going to be equal to 32 electrons. 7 times 4 is 28, plus 4 is 32. Carbon goes in the middle. There are 4 chlorines around it. 1, 2, 3, 4. Put my chlorines. And now, make sure everything has an octet. So this chlorine has 2, 4, 6, 8. 2, 4, 6, 8. 2, 4, 6, 8. 2, 4, 6, 8. And the carbon has 2, 4, 6, 8. Everybody's got an octet. Do I have 32 total electrons? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. We do have our 32. There are 0 lone pairs around the center. Okay, yes, there are lone pairs around the chlorines, but we only care about the center atom to find our molecular geometry. Notice it's a carbon with 1, 2, 3, 4 bonded atoms around it. So here we go, 4, and none of them are lone pairs, and so this will be tetrahedral. Again, tetrahedral. And then each of these are different. They're not identical to each other, so these bonds are all polar. All right, let's try this one. Carbon has 4 valence, plus oxygen is 6 times 2 of them, and so that's going to equal 16 electrons. We have a carbon in the center. It's surrounded by 2 oxygens, so I'm just going to draw 1, 2. Oxygen, oxygen. All right, let's start with this oxygen. It needs an octet. So far, it only has 2. But we have to be careful in this case because the carbon is going to have 4 bonds around it. And so we're going to note that this is a special molecule. When you have a carbon that has only 2 things around it, it's going to have 2 double bonds. Because you'll notice none of the carbons have lone pairs. You should never have lone pairs on a carbon atom. So it should have only bonds, and we need 4 total. So this is going to be 2 double bonds, and you'll notice that the common bonding for oxygen is a double bond with 2 lone pairs. to give it its octet. So now we have 2, 4, 6, 8, 2, 4, 6, 8, and that's going to be the Lewis structure for CO2. No lone pairs on the center, and the molecular geometry, it's got 2 things around the center, and so that is going to land us here, only 2 things around the center. That's linear. So we'll say linear. Because carbon and oxygen are different from each other, they are polar bonds. H2CO, hydrogen has 1 valence times 2 plus carbon has 4 plus oxygen has 6, which makes 12 electrons. And again, look at the beginning of the video if you don't remember where we're getting these valence from. Carbon is the center atom, so we have carbon in the middle. It's surrounded by 2 hydrogens, 1 oxygen. 1 oxygen and 2 hydrogens. Does not really matter where you place your hydrogens and your oxygens, just 3 things around the center. Now, hydrogen can only have 1 bond, so those are good. Your carbon here needs an octet. So far it has 2, 4, 6. Remember, you cannot put lone pairs on the carbon, so it needs another bond, and that bond is going to be with the oxygen. So now carbon has an octet, 2, 4, 6, 8, and oxygen needs an octet, 2, 4, 6, 8. And so now everything has octets or duets. Now I'm going to count my total. 2, 4, 6, 8, 10, 12. Got my 12, so that's good. How many lone pairs on the carbon or the center atom? None. So this carbon is surrounded by 1, 2, 3 bonded atoms. So 3 bonded atoms around it. None of them are lone pairs, and so this one is trigonal planar. So we'll say trigonal planar. These bonds, those are different elements, and in this bond, these are different elements, so all the bonds are polar. Okay, OF2, oxygen has 6 valence plus 7 for fluorine times 2 of them is equal to a total of 20. 7 times 2 is 14 plus 6 is 20. O is going to be in the middle. It is surrounded by 2 fluorines, 1, 2. So we're going to put our fluorines. Now give everybody an octet. 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. Everybody's got an octet. We've got a lone pair on top and bottom of the center atom. Let's make sure our total adds up. We have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Total is good. There are 2 lone pairs on the center. If you'll notice, we have 1, 2, 3, 4 things around the center because we count the alien heads. So when you have 4 things around the center and 2 of them are alien heads, it's going to be called bent. So this one is bent, and the bonds are polar between oxygen and fluorine. Okay, NH3, nitrogen has 5 valence plus 1 for hydrogen times 3 is equal to 8 electrons total. Nitrogen is in the middle. It's surrounded by 3 hydrogens, 1, 2, 3. Hydrogens each have 1 bond, and that's good. Nitrogen, we need an octet. 2, 4, 6, 8. There's the octet. That's a lone pair on the center, so it gets an alien head. Do I have my total of 8? 2, 4, 6, 8. Yes, I do. How many lone pairs on the center? Just 1. Molecular geometry, I have 1, 2, 3 bonded atoms, and 4, an alien head. So we have 4 things around the center. One of them is an alien head or lone pair. That's called a trigonal pyramidal. So this is trigonal, I'm abbreviating a little bit, pyramidal. And then nitrogen and hydrogen are different from each other, so these bonds we'll call them polar. Here's our last few. Hopefully you're getting the hang of it. I would like for you to pause the video, draw them out as best you can. This one's going to be a little bit tricky, and then unpause the video to see the final answers. And here are the final answers. So we have 26 electrons. Make sure that you put your 3 fluorines around. And then to have an octet on the nitrogen, we need 2, 4, 6, add a lone pair to have 8, and then 3 lone pairs around each of the fluorines. There's only 1 lone pair on the center. That makes this trigonal pyramidal. The bonds are polar. This one was a little bit tricky. Carbon was in the middle. It has hydrogen and nitrogen on either side of it. Hydrogen can only have 1 bond. But the carbon needs 4 bonds total, so that means that between the carbon and the nitrogen, there must have been a triple bond. And so that gives us 4 bonds on carbon. And then on the nitrogen, we needed 2, 4, 6, 8. One more pair to make sure that there was that octet. 0 lone pairs around the center. This is linear. The bonds are different here and different here, so they're all polar. And then finally for water, you have your oxygen, your 2 hydrogens, single bonds to the hydrogens, and then we end up with 2, 4, 6, 8, 2 alien heads around the center, which means that this is bent and the bonds are polar.